Hello, my dear students. I welcome you once again to this current lecture. In the last lecture, we studied the variation of equivalent and specific conductance with that of the concentration and dilution, how this concentration and dilution can affect the value of equivalent and specific conductance that we studied. Now, in the current lecture, we are going to study what is meant by equivalent conductance at infinite dilution. What is meant by the equivalent conductance at the infinite dilution, that is a lambda 0. What is the meaning of this? So, in the last lecture, we discuss about the variation of this equivalent conductance with that of the concentration by considering one equation, that is lambda is equal to lambda 0 minus b into under root c. So this is a one equation is there, as well as we know the equation for this lambda also, that is the lambda is equal to ls into 1000 divided by c. So these are the two equations for this equivalent conductance. So we are interested to consider this equation number first, that is this lambda is equal to lambda 0 minus b under root c. Now if we say that equivalent conductance at infinite dilution, so what is the meaning of this? So if we study literally, so literally what it means, if we consider this equivalent conductance at infinite dilution, so what does it mean? It means that if we consider by this equation, so if we want to get this infinite value, at that time what we have to consider? We have to consider this c must be equal to 0, then and then only we get the equivalent conductance at the infinite dilution. When concentration is equal to 0, at that time we hope that that conductance is called as the equivalent conductance at the infinite dilution. But we know that no any solution is there we have the concentration equal to 0. So this type of assumption is not a correct. No any solution is there with 0 concentration. Then the question arises, what is meant by equivalent conductance at the infinite dilution? What does it mean? So it is very simple. We have to consider the equivalent conductance. We have to consider equivalent conductance at a that particular concentration, at that particular concentration, which gives a complete dissociation of the electrolyte. When complete dissociation of electrolyte is there, when complete dissociation, when complete dissociation of electrolyte is there, when complete dissociation of electrolyte is there, then what happens? At this situation we can say that that dissociation is complete. That dissociation is obtained at dilute state, at the dilute stage. It must be the extreme dilute stage. It must be extreme dilute solution. So you can say that at the extremely dilute solution, what happens? The complete dissociation of an electrolyte can be takes place. So at that situation, we can say that no further dissociation can be observed or can be occur for the electrolyte, and at that situation, the the conductance, that is equivalent conductance shown by the electrolyte, is called as the equivalent conductance at infinite dilution. What is the meaning of this? When we consider that the complete dissociation of an electrolyte can be takes place, at which situation? At extremely dilute solution. At extremely dilute solution, that electrolyte get 100% or it get the completely dissociated, and at that situation the equivalent conductance shown by the electrolytic solution is called as the equivalent conductance at infinite dilution, and the solution is called as, and that extremely dilute solution is called as the infinitely dilute solution. It's called as the infinitely dilute solution. It's called as the infinitely dilute solution. So these are the two important concepts. One is a equivalent conductance at infinite dilution, that is a lambda 0, and second is a infinitely dilute solution. So what is by infinitely dilute solution? Whenever we increase the dilution of a particular electrolytic solution at a one stage, we get the complete dissociation of the electrolyte, and that particular dilution of an electrolytic solution is called as the infinitely dilute solution. And the equivalent conductance given by such a type of the infinitely dilute solution is called as the equivalent conductance at infinite dilution of an electrolyte. So suppose now after studying these simple concepts, now if we want to calculate this lambda 0, this equivalent conductance of an at infinite dilution is denoted by this lambda 0. This lambda 0 is called as the equivalent conductance at the infinite dilution. So if we want to calculate this equivalent conductance at infinite dilution for strong electrolytes, then how to calculate that? So these type of the lambda 0 values can be calculated with the help of the previous graph. We studied one graph in a previous lecture, that is the graph of this lambda versus under root c. So in this graph, for strong electrolytes we get such a type of the straight line nature. So if we extra plot this graph, what happens? We get the intercepts, of this graph on this y-axis. Then such a type of the intercepts, in this case it gives the intercepts, then the point at which it intercepts along this y-axis is called as their respective lambda 0 value. This is called as respect to lambda 0 value, and this is nothing but the equivalent conductance at infinite dilution for the strong electrolytes. So in order to calculate this lambda 0, we have to plot a graph of this equivalent conductance with that of the under root c, that is a concentration. We get a straight line nature for the strong electrolyte. If we extra plot this straight line nature, it intercepts along the y-axis, and from this point we get the magnitude of this lambda 0, that is the equivalent conductance at infinite dilution for strong electrolytes. So in this way we get the different values of this particular lambda 0 in per ohm centimeter square for different electrolytes, for different strong electrolytes. For KCl the value is 149.86, for HCl it is 426.16, for AgNO3 it is 133.36. So from this tabular data we can say that this HCl is called as the most strong electrolyte at as is give the value equal to 426. After that this KCl is a strong, and the least strong electrolyte among these is a silver nitrate. It gives the value of 133.36. So this type of equivalent conductance for strong electrolytes can be obtained with the help of the graph versus lambda versus under root c. So this is regarding the equivalent conductance at infinite dilution. Now after this we have to look towards the next important part from this chapter, that is one law is there. That law is called as the Kohlrauschs law of independent migration of ions. So this is one important point from this chapter, Kohlrauschs law of independent migration of ions. Now in order to study this law we have to consider this tabular data. So this table consists of the three different columns. In the first column electrolyte is there, in the second column lambda 0, that is equivalent conductance at infinite dilution in per ohm centimeter square are given, and in the last column the differences in this lambda 0 values are given between the pair of electrolytes. So first of all, if we consider the first pair of this electrolyte, that is a KCl and NaCl. In this pair of electrolyte what happens? The anions are common, but we vary the cations. We change the cations but anions are common. So this KCl gives the value of lambda 0 at at infinite dilution. It gives the value of 130, while NaCl gives the value of 108.9. Now if we take the difference between this lambda 0 value for both these electrolytes, it comes out to be 21.1. Now if we take the another pair of electrolytes, that is a KNO3 and NaNO3. In this case what we change here? Just we change again the anion. In the first case anion is a chloride, but in this case now anion is a NO3 minus. Again anions are the same, just we change the cations. So again it gives the value of 126.3 and 105.2. Again if we take the difference between these two lambda 0 values, again that difference is equal to 21.1. And the last pair of these electrolytes, if we take the half K2SO4 and half mole of Na2SO4, again if we consider this their lambda 0 values, again the difference is the same, 21.1. Now by observing all these values of lambda 0 and their particular difference, we can say that no doubt we can change the pair of the electrolytes by taking the common anion by varying or by changing the cations, even though we get the similar type of difference. We get the similar type of difference in their lambda 0 value at a given temperature. So what does it mean? So from this we can say that this type of the contribution of each ion, this type of the contribution of each ion towards the particular lambda 0 value is a fix. The contribution of each ion towards this lambda 0 value is a fix, and it is independent. It is independent upon its co-ion with which it is it associated or with which it is attached. So we can say that this type of the independent nature of each and every ion contributes the similar difference. It contributes the similar difference between the lambda 0 values at a infinite dilution solution. So due to which one law is given by the scientist Kohlrausch, and that's why it is called as the Kohlrausch law of independent migration of ions. Why it is independent? Because each and every ion has its own fixed contribution towards the lambda 0 value, which is independent upon the nature of the co-ion. So this is called as the Kohlrausch law of independent migration of ions. So according to this law, it states that at infinite dilution, what happens? Each ion at infinite dilution, each ion migrates independently. Each ion migrates independently. Each ion migrates independently of its co-ion, of its co-ion, and contributes to total equivalent conductance of an electrolyte, at definite share. So this is a simple law and simple statement. At infinitely dilute solution, each ion migrates independently of its co-ion. It is independent on its co-ion and contributes to the total equivalent conductance of an electrolyte at a definite share. So that particular law is called as the Kohlrausch law of independent migration of ions. Now according to this Kohlrausch law, the lambda 0 value, according to Kohlrausch law, the lambda 0 value for an electrolyte can be given by the equation lambda 0 is equal to L0 plus L0 minus, where this L0 plus stands for equivalent ionic conductance, equivalent ionic conductance. It is a equivalent ionic conductance at infinite dilution, dilute infinite dilution of cation, equivalent ionic conductance at infinite dilution of cation. On the other hand, this L0 minus is again equivalent ionic conductance again at infinite dilution, at infinite dilution of anions. So by observing this equation, we can say that the particular lambda 0 value for each and every electrolyte is nothing but the combination of the contribution of cations and anions present in a particular electrolyte. So this type of the contribution is called as the equivalent ionic conductance at infinite dilution of cations and anions respectively. So in this current lecture, we studied the two important points from this chapter, that is called as the equivalent conductance at infinite dilution. What is the definition or what is the meaning of this? So you can say that whenever we consider the complete dissociation of an electrolyte at the extremely dilute stage, so that particular conductance is called as the equivalent conductance at infinite dilution, and that solution is called as the infinitely dilute solution. After that, we studied how to calculate this lambda 0 for strong electrolytes. So for this purpose, we have to take the help of the graph of this lambda versus under root c. From this graph, if we extra plot the straight line nature of this graph, we get the intercepts along the y-axis, and from these intercepts we may calculate the lambda 0 for strong electrolytes. So for this purpose, we consider this type of the different lambda 0 values for the different strong electrolytes. And finally, we consider one important law from this chapter, that is called as the Kohlrauschs law of independent migration of ions. For this purpose, we consider this type of the tabular data, in which we take a pair of electrolytes having n common, but they get vary in terms of their cations. They give the fixed value of this lambda, even though they have the similar type of the differences between each and every pair. So from this we can propose the law, that is the Kohlrauschs law of independent migration of ions. And according to this law, each ion migrates independently of its co-ion and contributes to total equivalent conductance of an electrolyte at a definite share. So that is the statement for this law. And according to this law, the equivalent conductance at infinite dilution for an electrolyte can be given as L0 plus L0 minus, where this L0 plus and L0 minus is nothing but the equivalent ionic conductance at infinite dilution of cations and anions respectively. So this is the point of current lectures discussion. So remaining points from this chapter we will take in a next lecture. So with this I stop here. Thank you so much.